Reducing the carbon footprint, sustainable lithium battery recycling strategies for the electric vehicle supply chain. Introduction. Electric vehicles, EVs, are crucial for sustainable transportation, addressing climate change and reducing greenhouse gas emissions, particularly from the transportation sector, which contributes roughly 24% of global CO2 emissions. EV adoption offers a significant emissions reduction compared to traditional vehicles, further enhanced by integrating renewable energy sources into the electricity grid. However, the sustainability of EVs is challenged by the environmental impact of lithium-ion batteries. The extraction of metals like lithium for these batteries raises concerns about resource depletion and environmental, social, and governance issues. Lithium mining, specifically, is associated with ecological damage, including habitat destruction. To mitigate these challenges, lithium battery recycling is essential. Recycling minimizes environmental harm, reduces reliance on newly mined materials, and lowers the carbon footprint of the EV supply chain. Result and discussion. Components of electric battery. Lithium, crucial for EV batteries, is sourced from brine deposits and hard rock ores. Brine extraction via solar evaporation, though common, is environmentally damaging due to its lengthy process, dependence on evaporation ponds, and use in arid regions. Cobalt and nickel, often co-extracted from nickel sulfide ores or as copper mining byproducts, present their own challenges. Cobalt extraction is linked to ethical concerns, particularly labor practices in the Democratic Republic of Congo, a major supplier. Nickel mining, often using pyrometallurgical and hydrometallurgical methods, contributes to deforestation and habitat loss, notably in Indonesia. All three metals are projected to see increased supply by 2030, driven by the growing EV and battery technology markets. The varying projected increases likely reflect differences in demand, resource availability, and production capacity. The ranges provided for 2030 acknowledge the uncertainties inherent in long-term forecasting within the dynamic material supply and demand landscape. Environmental harm. Mining's environmental impact is complex and far-reaching. It can fragment ecosystems, destroy landforms, and cause biodiversity loss. Weak regulatory enforcement often leads to disregard for ecosystem preservation, necessitating complex post-mining landscape restoration. Furthermore, mining removes plant cover and topsoil, disrupting local ecosystems and increasing erosion and sedimentation in water bodies. This, in turn, harms aquatic life and degrades water quality. Mining significantly degrades soil and accelerates erosion, with severe environmental consequences. Surface mining, in particular, often strips away topsoil, essential for fertility and vegetation, causing immediate erosion and disrupting the area's water balance. This loss of vegetation exposes the soil to wind and water, further intensifying soil loss. Mining operations also introduce heavy metals and pollutants, like arsenic and lead, complicating recovery and persisting long after operations cease. These impacts lead to biodiversity loss and ecosystem disruption as habitats are destroyed and species decline. Therefore, comprehensive mining management and restoration strategies are crucial for environmental health and sustainability. Sustainability. The digital revolution and growing EV market place immense pressure on the mining sector to balance resource extraction with sustainability. Meeting the increasing demand for lithium-ion batteries requires responsible practices to mitigate long-term impacts like environmental degradation and biodiversity loss. Green mining, promoting sustainable extraction, is crucial. While essential for EVs, lithium, cobalt, and nickel extraction carries environmental costs like deforestation and pollution. Sustainable techniques like backfill mining and community involvement can minimize these effects. Proper mine closure, including restoration and social programs, is also vital. Beyond sustainable mining, a circular economy approach, especially battery recycling, is key. Recycling reduces reliance on virgin materials, lowers energy use, and minimizes waste, even creating new economic opportunities. Sustainable practices improve regulatory compliance and market resilience. Balancing greenhouse gas emissions with raw material extraction for batteries is a major challenge. The entire lithium-ion battery life cycle, from sourcing to recycling, demands significant energy and contributes to emissions. Greenhouse gas emission. Lithium mining raises significant greenhouse gas emission concerns, both from direct extraction processes and indirect emissions from lithium processing. Furthermore, lithium-ion battery production, particularly for EVs, adds to this issue. The battery life cycle requires substantial energy in materials, contributing to further emissions. Circular economy strategies, like recycling steel and plastic components, can improve battery production sustainability. Future EVs are expected to have a lower global warming potential thanks to advancements in energy and steel production, such as hydrogen-based steelmaking, which could further reduce emissions. Reducing strategies. Recycling spent lithium batteries is crucial for reducing demand for lithium and other valuable resources, addressing both environmental and economic concerns. Traditional recycling methods, like pyrometallurgy and hydrometallurgy, are energy-intensive and unsuitable for all cathode materials, highlighting the need for direct recycling techniques. Direct recycling, involving cathode regeneration through chemical lithiation at room temperature, offers a promising, energy-efficient, and cost-effective approach. Green methods using organic acid mixtures have also been developed to reclaim lithium and purify graphite, improving regenerated material performance. Novel methods like magnetic nanohydrometallurgy, using magamite nanoparticles, enhance lithium recovery from spodumene residues, achieving high efficiency and promoting sustainable lithium recycling. Policy and regulation. EU battery regulations balance environmental, economic, and geopolitical interests, focusing on life cycle management and due diligence. However, they face criticism for prioritizing EU interests and potential disadvantages to producer states. Proposed regulations aim to limit battery carbon footprints. International interest in resource circulation and carbon neutrality is growing. While sustainability principles are integrated, gaps remain, particularly in data availability for life cycle environmental impact assessments and varying implementation of recycling regulations. Recommendations include requiring thorough environmental impact documentation, promoting alternative batteries like sodium-ion, enhancing recycling initiatives, strengthening mining regulations, and advancing circular economy principles through battery reuse and repurposing.